And do this. We'll go over a few things and we'll just kind of continue with this topic. So delta G, remember, is Gibbs free energy. And at towards the end of lecture or the middle of lecture Tuesday, we introduced this equation that you see right up front here. Delta G equals delta H minus T delta S. Now this is the overall big picture way to answer that question. Will a reaction happen or not? Well, we can figure out the sign on delta G, and that will directly tell us if delta G is, does anybody remember, if delta G is positive or negative, which one means that a reaction is favorable or spontaneous? Sorry, let me pull the chat up. Somebody may be typing it as well. Yes, negative. If delta G is negative, that is a favorable reaction, okay? So that's a direct way to tell. So we're just going to continue with this problem. On the homework, I've gotten some really good questions on the Chapter 7 homework from some students that are very diligent. So all that to say, if you're one that tends to procrastinate, don't do it, because I'm not as good with my email on the weekends as I am on the weekdays. So please take some time this evening or tomorrow to look at that Chapter 7 homework and send me emails and questions. I think it's not due till Monday at midnight, so you also do have some time Monday, but don't put that homework last minute because it's not necessarily an easy thing. Okay, so let's look at this problem right here. We have calcium carbonate. It's a solid decomposing into calcium oxide and CO2 gas. And here is the delta G that we're given for that at 25 degrees Celsius. The first question here is the reaction spontaneous at 25 degrees Celsius? We don't even have to do any math for this. What do you guys think? Is it spontaneous? So you can just type yes or no, or say yes or no. See some people shaking their heads. What do y'all think? Anybody else? How do we know? How do we know the answer to this question? All you do is you look at the sign on delta G, right? Delta G is positive. And if we go back up to that table, here's how you know. If delta G is positive, let me erase so you can see clearly on this table. That's column 2 or row 2. If it's positive, that is non-spontaneous. Okay, so this reaction is not spontaneous at this temperature. At this temperature, is the reaction spontaneous? No. Okay, the second question is, does entropy, remember what is entropy? Entropy is delta S, delta S. Is entropy increasing or decreasing? Is delta S positive or negative? Remember, entropy is another word for disorder. Jenna says it's increasing. Anybody think differently? Here's what I notice is that we have only a solid on our reactant side, and look at the states of matter on the product side. They're all gases. You guys remember the levels of disorder that are inherent to these different states of matter? We said solids are most ordered, gases are most disordered. So if you have solid and you're making gases, you are becoming more disordered. So entropy is, I agree with Jenna, it's increasing here. Okay. Additionally, another way you could look at it is I have, this looks balanced. I have 1 mole or 1 item on my reactant side, and I have 2 moles of stuff, 2 different products on my product side. So you're just making more things. That's inherently disorder as well, more disordered. All right, so entropy is increasing. Question 3 is the trickiest. This is more of a concept thing here. Do you expect the reaction to be spontaneous at higher temperatures? Right now at 25 degrees Celsius, it's not spontaneous, not going to happen. Could it become spontaneous at higher temperatures? How do we know this? How do we know? How do we know? So we do kind of a thought experiment. Right now we know that delta S is positive, and I'm gonna move this over actually, because we know delta G is positive, and we know delta G equals delta H minus the temperature times delta S, okay? So we don't know the sign on delta H, okay? But we do know delta S is positive, but you also have to consider this minus sign. There is a minus sign in this equation right in front of the T delta S term. We know temperature will always be a positive number. We can never have a negative Kelvin. So because you have two positive things in this, that minus sign makes that whole term negative, right? The minus sign makes this whole T delta S term negative. And that mathematically is in favor of a negative delta G, okay? However, your delta H here must be a positive number. It must be. If we have a positive delta G, and this minus sign right here would make this whole term negative, then what that means, to get a positive number over here, our delta H has to be positive, or there's no way we could get a positive delta G. Okay, so if you're tracking with me, our delta H, what we've just figured out, is positive. So the question is, could this reaction become spontaneous? Could we get a negative delta G at higher temperatures? So I'm just gonna plug in a few simple whole numbers here as a thought experiment. Let's actually do an experiment. Let's plug in some simple numbers for our delta H, our temperature, and our delta S, okay? I'm gonna plug in the number 10, a positive 10 for delta H. I'm gonna plug in a positive 1 for temperature. I'm just plugging in some simple whole numbers to do a thought experiment here. And I'm just gonna plug in a simple number 2 for delta S, okay? Just forget units right now. We're just gonna plug in some whole numbers. What value would we get for delta G? We know our delta H is, or our delta H and our delta S is positive, so that's why I plugged in all positive numbers here. What is our delta G? 10 minus 1 times 2. You should get a positive 8. Now let's ask the question, at higher temperatures, could delta G become negative? Well, let's raise the temperature. Let's raise it by a lot. Let's say times 20. So now we're gonna plug in 20 for our temperature. I'm not gonna change anything else. Do 10 minus a much higher temperature, 20 times 2. Now what do we get for our delta G? Now, Jenna said we get negative 30 because 20 times 2 is 40. 10 minus 40 gives you negative 30. So what just happened? At higher temperatures, delta G became negative. It did become spontaneous. So I'm gonna go back up to that table that we filled out on Tuesday, and we're gonna make a note. And I would encourage you to make this note and have it available for the exam as well. What category we're in with our delta H and our delta S, the signs, corresponds to row 3, a positive delta H and a positive delta S. And the problem we're just doing, that's what we had, positive delta H and a positive delta S. And when you have that, we don't know what delta G is. It honestly depends on what the temperature is doing. So this reaction, this scenario, the equation or the reaction will tend to be spontaneous at higher temperatures. So you can say tends to be or become spontaneous. I'm just going to abbreviate SP at high temps. Notice I'm not using the words always here, but it will tend to become spontaneous at higher temperatures. It can tend to be non-spontaneous at lower temperatures, vice versa. All right. So that's what you know at about row 3. Now on 4, it's just the exact opposite. 4, this column or this row right here, when you have both negative, those types of reactions, when you have a negative delta H and a negative delta S, those will tend to be a favorable or a spontaneous reaction at lower temperatures. So I don't really have a whole lot of room to write that. I'm going to draw my arrow up here. Sorry, and write it more clearly for you on your sheet, however works best. But tend to be spontaneous, SP, at lower temps. Now, the reason I'm going over this and taking the time to do this is because there's some homework questions where it kind of asks you these similar things. I got an email about one, okay? And this is the kind of thought stuff you need to think through. It's actually very hard to explain unless we're looking at and plugging numbers in ourselves, simple whole numbers, like I said. But hopefully that will help you with a couple of the homework questions on chapter 7. Any questions on that so far? Okay. I actually left this whole slide blank because I was going to do all of that little math stuff on this slide, but I don't think we need it. So, oh, I didn't answer number 3. The answer is yes. Yes, we would. Okay. All right, well, I'm going to move on. We're going to do another practice problem with delta H or delta G, and then we're going to move on to a different topic. We'll be done with talking about Gibbs free energy for the moment and move on to reaction rates. So here's a problem where we have a reaction here, very vague reactants and products, A, B, and C. We have some solid substance that we're calling A, and it's breaking down into B and C, two different products. So here's an example. This is a solid, this is A, and here's what it looks like. It's just giving you a picture of those green spheres, and it's breaking down into two different things. Here's our key over here. A is the green spheres, B are the faded green spheres, and these are C. And C is a gas. We know it looks like a gas because those spheres are filling, expanding to the size of the box. That's what a gas does, takes up the space and volume of the entire container. But B is still a solid, and it's organized down there in the bottom. Here's our delta H, negative 23.5 kcal per mole. What is the sign on delta S? Anybody? Positive or negative? Kathleen says positive. Anybody agree or disagree? Well, you're going from just one thing to two things. That's inherently more disorder. And then you're going from a solid to a solid plus a gas, and a gas is inherently more disordered. So your delta H is positive. All right, second question. Is the reaction spontaneous at all temperatures, some temperatures, or no temperatures? What do you guys think? How do we answer a question like this? Kathleen says all temps. Jenna says some. How do we answer a question like this? What do we need to consider? You actually don't have to do any math. Aaliyah says all. How do we know? Delta H is negative, and delta S is positive. So remember, when you have a negative delta H and a positive delta S, if you go back up to the table, that corresponds to row 1. And when these are the cases, mathematically, you will always get a negative delta G, always. And that means it is going to be spontaneous no matter what the temperature is doing, at all temperatures, because your delta H is negative, your delta S is positive. So no math on a question like this. It's just understanding the mathematical concepts of the equation. Any questions on that? I'm telling you, that table will be very handy for you with your homework and with the exam. Okay, so we're going to put a cork in delta G for a second. We're going to talk about reaction rates, and we'll come back to delta G stuff when we talk about equilibrium. Okay. Reaction rates. So all of chapter 7, if you haven't figured out by now, is trying to figure out how do we know if a reaction will happen. So we've actually answered that question now. Depends on, from an energy standpoint, delta G is the short answer, if delta G is positive or negative. But we want to know, just because a reaction we can say can or cannot happen, what if it will happen? Does that mean it's going to happen in a timely manner? Okay. So delta G tells us if a reaction will happen, but not how fast. So there are some reactions we can think of, like stuff decomposing in landfills. Okay, decomposing is a reaction, right? But does that happen very quickly? No, it takes years and years and years. It's actually a big issue that we have to think about, okay? That's why you should recycle, okay? Little plug there. But some reactions are going to happen very slow. Some reactions on the flip side happen very fast. Okay, our body depends on some of these things. Like, for example, if we were to get real technical, if you think about in your lungs, when you breathe in oxygen, everybody take a deep breath. You just breathe in oxygen, and immediately that oxygen had to bind to hemoglobin. Okay, immediately, right? And so some reactions happen very fast, and immediately your blood also has to let go of CO2, and that transaction with oxygen and carbon dioxide has to be a very quick reaction. So we need to think about the speed of reactions as well. Why? Because our body has to think about that all the time. So the rate or the speed of a reaction is determined by this phrase we use called efficient collisions. Efficient collisions. Molecules colliding are how reactions happen. And molecules can collide and you not get a reaction. So that must mean there has to be something proper about the collision for the reaction to happen. So what is an efficient collision? It's a colliding of two molecules with two things: correct orientation. They have to be facing the right way. The right atoms have to bump into the right atoms. And sufficient energy. All right. They have to have enough energy they have to collide forcefully enough for a reaction to happen. An example down here, anybody ever studied the ozone? What's happening to our ozone layers in the atmosphere? Well, they're probably a lot better than they were in the 80s, right? Everybody heard the joke that hairspray destroyed our ozone layers from the 80s. This is actually a picture of ozone right here. O3, that's a molecule of ozone deteriorating. Ozone, another molecule in our atmosphere, is nitrogen monoxide, so NO. So this picture is showing you an effective collision between a molecule of ozone and a molecule of nitrogen monoxide. And in that effective collision, look what I noticed. The blue sphere, nitrogen, has to be facing the ozone molecule. All right, and when that happens, they're here collided. Here's the ozone molecule, O3, and there's nitrogen monoxide. And then you create a molecule of oxygen and nitrogen dioxide. Okay, this I'll do it in green. This oxygen just traded molecules. All right. Now, what if these collide, but this time the oxygen is facing ozone? If that happens, I know that seems very small and technical, you'll get no reaction. Okay, that's what we mean by an efficient collision. It's got proper orientation. The right atoms are facing the correct way. Now, correct energy or sufficient energy is also a part of this. And we're going to look at that in more detail in just a second. But to understand reactions and reaction rates, we're actually going to get into something we call diagrams, reaction diagrams. So I'm going to draw an example of a reaction diagram. You need to know how to draw these for the exam. Okay, so draw this out with me. Here's an example. Any reaction diagram that we're going to look at, it's a plot. It's a plot of the reaction on a graph. Okay, so we're going to look at how reactions happen from a graph standpoint. So I'm going to draw just a little X and Y axis. And on the x-axis, this is the reaction progress. Okay, from beginning to end. And on the y-axis, this is going to be, I'm going to write delta G. This is going to be our level of free energy. Okay. So every reaction diagram have the same x and y axis. Your energy on your y-axis, your reaction progress on the x-axis. They also have a energy marking for reactants and products. Our reactants have a certain amount of energy trapped within the bonds, and then when we reform our products, those products have a certain amount of energy trapped within their bonds, and the energy is different usually. So we'll just put some random markings. Let's say our reactants, I'm going to put an R for reactants, have this amount of energy starting out. I'm just doing a very vague kind of general analysis here. And let's say our products, when we form the products, they're lower in energy, they're more stable. That's favorable, that's good, right? Let's say they have that amount of energy. So all this to say, every reaction diagram, you have to mark off your spot for your reactants and your spot for your products, the starting and the ending point. And then somewhere through there, any reaction is going to start off with a certain amount of energy that you have to clear, okay? So it all starts off with this kind of upward peak. You're going to draw your reaction progress towards a peak, and then it should level off down at your products, okay? Now, here's what I'm going to say. Not every reaction diagram will look exactly like this, okay? Because some reactions, we'll draw another one in a second, some of them may have products with different levels of energy. But every reaction diagram should have the reactants marked off and the products. And guess what? Another thing we can mark off, that energy difference between reactants and products. Guess what that energy difference is called? We call that delta G. That is the change in free energy. That is delta G. What can you say about delta G for this reaction? Is delta G positive or negative here as you go from reactants or products? That's right, Brennan, it's negative. You start off with a higher amount of energy, you end with a lower amount of free energy. So the change here is negative. All right. Now let's draw another reaction pathway. Let's say we start off with this amount for our reactants, but let's say our products, when we finish for a different reaction, our products have that much energy. Well, again, every reaction starts off with an energy peak, and then it's going to level off, and that peak has to be higher than the energy level of the products. Okay, so you get a totally different reaction pathway. Reaction pathways can look all kinds of ways, but we still can mark off our delta G. Go ahead and try to mark off your delta G here. It should be the difference in the energy level between reactants and products. So if I draw a little dotted line out here and a little dotted line over, the difference between the reactants and the products, that's the delta G for this reaction. Is this delta G positive or negative? As you go from reactants to products, this one you're increasing. There we go. Thank you, Aaliyah. It's positive. Okay. So I just wanted to introduce a few just bare bones things about reaction diagrams so that you hopefully understand them better. But be prepared to draw these out for the exam, okay? All right, and then you could label these exergonic or endergonic, right? You could tell me which one's exergonic and which one is endergonic. Don't forget those vocabulary terms. A negative delta G is exergonic. A positive delta G is endergonic. So if I ask you that, you could tell me. All right, and then there's another thing we're going to introduce about reaction diagrams called activation energy, okay? That is the amount of energy that you have to clear. That's the peak that we drew, all right? So it's actually, if we look, the next slide has 3 different kinds of reaction diagrams drawn out. And to further understand the rate of a reaction, how fast it will go, it all depends on the activation energy, okay? That is EACT, so we'll just fill this in, ACT. Activation energy. All right, that is the amount of energy required to begin the reaction. So the reaction has to clear that energy level so that, or it won't make the products if it does not. If it does, it will make the products. And if you're looking at this reaction diagram, A right here, notice we have our level of our reactants marked off and the level of the products, okay? And the activation energy is right here. What we're saying, the activation energy is the level from reactants up to the peak of the reaction pathway. That difference from there down to the level of the reactants, that's the amount of energy that you have to clear for the reaction to happen. That's the activation energy. And you can draw that for any reaction. You just start at your reactants, draw it up to the peak. That difference is your activation energy. Okay? It's determined by how efficiently molecules collide, and the activation energy determines how fast the reaction goes. Okay? Now notice your activation energy can be different for any reaction pathway. So a small activation energy means a fast reaction. You don't have to clear a big energy hump or peak. A large activation energy is going to be slower. Whoops. Means a slow reaction because you got to have a lot of energy before you can make that reaction happen. So if you're looking at A, B, and C, which one do you think is the fastest reaction? Fastest rate? I wish I would have made this a poll question, but I did not. You can type it in the chat. You can unmute yourself. Which one looks like the fastest one to you? Jenna says C. Tucker says C. Yeah, everybody agrees. C is going to be the fastest. Because why? If you notice, the activation energy is the smallest. Very small. Which one's going to be the slowest, on the other hand? A or B? B, 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 B. Okay, B has a very large activation energy. Okay, super large. So B will be the slowest. Now, the last thing I want to point out, and perhaps the most important thing from this slide, is this right here. I'm going to box in this statement. The activation energy does not affect your delta G. Okay, it doesn't change it. It doesn't affect it. Delta G is a set thing. It's completely independent of activation energy. We can actually change the activation energy. I'm going to point out a way we can do that in a minute. We can modify. We have found ways to manipulate reaction rates. So we're going to look at 3 ways we can using our own power and tools in the lab or whatever, in our bodies do this. We can, if a reaction's slow and we want to speed it up, or if a reaction's really fast and we want to slow it down, we have ways we can do that. Okay. So that's the next couple slides. That's what we're going to talk about. How can we modify reaction rates? How can we make them more efficient? Okay. If we're going to digest our food, we need those reactions to happen relatively quickly, right? I don't know about you. I get hungry like every 3 hours. Okay. All throughout the day, I'm eating snacks. Okay. And our body's constantly digesting our food. If that was a very, very slow reaction, that'd be terrible, right? Like we wouldn't have to eat, but maybe once a week. That would be awful. Who wants a world where you only eat once a week? So what are different ways that we can modify things and make reactions happen in an efficient time, a time that our body needs them to happen? Well, one, we can change the temperature. That's actually the first thing you see right below. You can increase or decrease temperature. We're going to look at that, what that does to our reactant and product molecules. I'll make a note here. Increasing temp speeds up the reaction. And I really don't have space, but vice versa, decreasing temp slows it down. The second thing we can do is we can change the concentration of reactants. Okay. We can add more molecules. And if we're doing a reaction in a confined space, like a test tube or a beaker, the more molecules you have in there, the more they're going to collide with one another. Okay. And the more the reaction is given the chance to happen. Then lastly, we can add something called a catalyst. Anybody ever heard of this word before? Catalyst? Sometimes the more biology word that's used is the word enzyme. Okay. Enzymes are molecules in our body that we depend on. Okay. People with like enzyme problems or enzyme deficiencies, they have a lot of health problems. So your enzymes are the catalyst. Those are the things that make the reactions happen more quickly if our body needs them to be quicker. So we'll talk about that in a second. All right, so let's look at how does temperature affect reaction rate? Well, an increase in temperature, like we said, it speeds up the reaction, but how? Well, it increases the frequency. I'll say increases the frequency of collisions. What do you mean collisions? Well, collisions between our reactant molecules, they'll collide more often. Okay. If we have it in a box, imagine that we're doing a reaction in a container in a box. We have a confined space and we're speeding up how fast those molecules are moving. They're going to collide more often. All right. And it also increases the forcefulness of collisions. Okay. And what that does is that gives a better chance of meeting that activation energy. Okay. Remember, I said molecules have to have proper orientation and they have to have sufficient energy. And if you're increasing the forcefulness with which they collide, then you're giving a better chance that they'll have the right amount of energy they need to react. Okay. So we can increase temperature to increase reaction rate. We can decrease temperature to decrease reaction rate. Another way is changing concentration. If we increase the concentration of our reactants, we will increase the frequency of collisions between our molecules. And if we increase the frequency, we increase the chance of molecules colliding with just the right orientation so that the reaction will happen. And the more we do that, the faster the reaction will be, or the rate of the reaction. Okay, so if you increase the concentration of reactants, you increase the rate. But if you decrease the concentration, the number of reactant molecules, you also can decrease the rate. Okay, works both ways. Lastly, we said a catalyst can affect or manipulate reaction rates. What exactly is a catalyst? We gave an example, enzymes are a catalyst, but what is it? What does it do? How does it change our rate? It's just a substance that increases the rate, but is not altered. It is not a reactant, okay? It's not a reactant molecule. It just takes reactant molecules and it makes them collide, if that makes sense. It's not altered itself in the reaction. Reactant molecules, they are altered. Bonds are broken, they reshape, they reform. A catalyst, the way it does this, the way it manipulates the rate, is it essentially lowers the activation energy. And how in the world does it lower activation energy? Several different ways. It can create an entirely different new reaction pathway. We're going to draw examples in just a second of what that would look like. Or it can grab those reactant molecules and it can put them together the way that they're supposed to go together. Instead of that happening by random chance, the catalyst says, I'm going to make y'all. Did anybody have siblings growing up when y'all get in trouble? Your mom or your dad would be like, now hold hands and kiss and make up, right? I'm going to make you do it. That's what a catalyst does, okay? It's the mean parent that says, you guys are going to behave the right way. So it grabs those reactant molecules and it forces them into the proper orientation. Or it just simply brings the molecules close together and it gives them the chance to interact the right way so that the reaction will happen, okay? All right, let's draw two little examples in this diagram of a reaction with a catalyst or without a catalyst, and then a reaction with a catalyst. So we have our X and Y axis labeled here. I'm just going to go ahead and randomly assign reactant and product levels. There's the energy level of our reactants. There's the energy level of our products. And I'm just going to connect these two with an activation energy peak. So remember, you always have to have some kind of peak, and then it levels off where the products are. And now let's go ahead and actually define the activation energy. So remember, we define activation energy as the level between our reactants and the peak. So this right here, this difference on the y-axis, this is the activation energy. And we abbreviate activation energy, the energy of activation, ACT, EACT. Okay, so that is our activation energy. It is the difference, okay? Now, this is a reaction with no catalyst. We'll say no catalyst. I'm going to change colors here. If you have a different pen or something, grab it. Let's draw a reaction pathway with a catalyst. Remember, a catalyst lowers the activation energy. It does not affect delta G, so the level of energy with our reactants and products is going to stay the same. The only thing that's going to change is that peak. It's going to be lower. So what that would look like is we have a reaction, starts off here, and maybe it's just got a lower activation energy, and then same level on the products. So now the difference in energy between our reactants and the peak is right here. This is a much smaller activation energy. Okay, it's much, much smaller. And this reaction is with a catalyst. Okay, so it can speed up the rate of a reaction by lowering the activation energy. Okay, any questions so far on that? And again, these are what enzymes do. There's thousands of different kinds of enzymes. Proteins are enzymes. And there's many, there's like, our body has like 60,000 proteins. Now, not all proteins are enzymes, but a lot of them are. And like when we digest glucose, okay, there's tons and tons of steps as we metabolize glucose to get ATP. That whole chain reaction, if anybody's ever had a biology class, happens because of enzymes, okay? So we depend on these big time. All right. Okay, so that's it for, how are we doing on time? That's it for reaction rates and delta G. How do you guys feel like we're doing speed-wise? Am I just flying through this stuff? You guys grasping it? Any questions so far? Are y'all hanging with me? I'm looking at the chat. Nobody. Are y'all alive? Okay. So we're actually going to start with equilibrium since we have, what time we get done at 12:05? We still have almost half hour. So we may get through more of this than I thought. That's great. Does anybody need a brain break? Anybody need to disengage and re-engage for a second? I'm going to take a drink of water. Isn't there a presidential debate tonight? Anybody watching it? Or anybody think it's going to be a big old waste of time? Okay. Please, no. Well, we'll see. We'll probably watch it. I don't know if it'll help, but we might. Okay. Equilibrium. So this is a whole different topic. And I will tell you again, we're not out of the woods with chapter 7. This stuff is not necessarily the easiest thing to understand. So please ask questions if you find yourself confused. If you don't want to ask it in the chat, please email me your questions, but don't leave them unanswered. All right. So we've been talking about delta G, and we're actually going to bring delta G back into the equation now. We've been harping a whole lot on the sign of delta G. Is it positive? Is it negative? And what does that mean? Well, now I'm going to throw you a curveball. You ready for the curveball? What if delta G is 0? What if it's not positive or negative? What if it's 0? Well, what the heck does that mean? What if we have some equation A plus B makes C and D and our delta G is 0? Well, number one, we could actually draw a picture of that to help us give us a visual on an energy diagram. Okay, think about the reaction we've been drawing so far. In fact, let's go back up here. We drew 2 reactions, one with a negative delta G and one with a positive delta G. So what would it look like if our delta G is 0? There's no change on the y-axis. What would that look like on the reaction diagram? I'm going to go back down here. What that would look like is the energy level between our reactants and our products are the same. There's no change. We still have an activation energy, so we still have a little peak between the two. But essentially, the energy level of the reactants and the products are the same. They're not changing. So what does that mean exactly? What that means is we're going to have actually, instead of just one reaction happening, which is what we've drawn, we're actually going to have 2 reactions happening. Let's see where the second reaction comes from. Because you read this down here, both reactions occur. What do you mean both reactions? I thought there's just one reaction. A and B makes C and D. Well, that will happen. I want to read these statements. If I have a test tube and I mix A and B together, we know what they're going to do. They're going to make C and D. They will react. They will produce C and D. However, once enough C and D is made, because it's not energetically favorable to go one way or the other, remember what's favorable is a negative delta G. When your products are lower than your reactants, that's favorable. That's negative delta G. What's unfavorable is when the reactant of the energy level of the products is above the energy level of the reactants. But if they're the same, we can't say it's favorable to make the reactants or to make the products. They both will happen. Okay, once enough C and D is made, they can also collide. What's preventing them from colliding in our test tube? Nothing. C and D can collide, our molecules are always moving, and they can react to make A and B. That can happen, okay? I just blew your minds. I don't see any of those exploding brain emojis in the chat. That's what I should be seeing, right? This is called, what do we call this? It's called a reversible reaction. Oh, look at all those beautiful emojis. Y'all are cracking me up. I feel like a preacher that is like eliciting a hand clap or something in their sermon. Everybody say amen, okay? This is called a reversible reaction. So here's the 2 reactions. We have A and B make C and D. We now call this the forward reaction. And C and B colliding and making A and B, we call this the reverse reaction. Reverse. Okay. And combined, we can actually draw these 2 together. All we're going to do, you've probably seen this before in like textbooks or things. We're just going to draw a half arrow up and a half arrow back. This is indicating that both reactions are occurring, making C plus D. All right, so that is essentially, I'm setting you guys up to understand what, I haven't defined what equilibrium is yet, but when you have a reaction like this, now you can have something called equilibrium. Okay, equilibrium. So we still need to define what equilibrium is, but when you have a reversible reaction, you can have a system that will reach equilibrium. You cannot reach equilibrium with only a forward reaction. It has to be a reversible reaction to have equilibrium. Now I want to define something technical here because chemistry is that way, just the nature of it. Reversible reactions do not always have an exact delta G that equals 0, but can be very, 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 very close. Okay, so what that means is that you can see here slightly that this one's lower a little bit than A and B, the energy level. Okay, so delta G is not exactly 0, but it's pretty close. Okay. And when you have this, the favorable reaction, favorable meaning the one with a negative delta G, is what we write as the forward reaction. Okay, so I'm being technical here, but I want to define this for a reason. You can see here it's a little more exaggerated. Maybe this time A and B is a little bit lower. So this one, the delta G would be positive, and this one, the delta G would be negative. Okay. But the one that's the negative delta G is the one we write as the forward reaction. Okay. Now, when this happens, this is a very important phrase right here. I'm going to read this. Eventually, the rate of the forward and the reverse reactions will become the same. Eventually. So I want to do a little, I want to think about something with you. If I have a test tube, so I'm going to zoom in up here. I'll zoom out in a second. If you're writing, I'll be right back. Here's a test tube. And let's say in my test tube, I have all A and B. Initially, I just have all A and B. Well, the rate of the forward reaction is going to be dominant here. You're only going to make C and D, okay? So the rate of the forward reaction will be very fast because you have tons of A and B and they're all colliding and you're making some C and D. Well, eventually, you'll have a test tube that looks like this. You'll have a few molecules of A and B, but you'll also end up with a few molecules of C and D, all floating around, okay? All colliding. And eventually you're not going to make all C and D. You will never have a test tube where you're just going to end up with all C and D. That will not happen. You will finish this way. You'll just have, and you're not necessarily going to have equal amounts of A, B, C, and D, but the rates of the reaction will become the same. That's what this statement is saying. The rate of the forward and the reverse reaction will become the same. So let's talk about this a little bit more. At this point, the concentrations, and I'm going to define the word concentration. I actually haven't defined that word, and that's a very, very chemistry word, the word concentration. So we'll actually define that in a little bit. But what it's saying is at this point, whenever the rates of you're making A and B, or sorry, you're making C and D, and you're also remaking A and B, that's the rate. The concentrations of the products and reactants are not changing. That's like an incomplete sentence. At this point, the concentrations of the products and reactants, it should say are not changing, but they'll not be changing. Okay. This is also, I'm sorry there's a lot of writing. I really don't like slides like this, but it's kind of unavoidable with equilibrium. Let's read this. Both the forward and reverse reactions are still occurring. This is not a situation where nothing's happening. People can tend to think equilibrium is like, oh, things are just set, they're not changing. No, lots of things are changing. It's a very dynamic thing, equilibrium, because you have two reactions happening. Both the forward and reverse reactions still occur, but because they occur at the same rate, there's no change in concentration. Okay, eventually you reach set amounts of A and B and C and D because you're remaking A and B at the same rate that you're making your products C and D. This is called an equilibrium. All right. I told you equilibrium is hard. It's just, it's hard to understand. But hopefully in these next couple slides, it will become a little more clear. Any questions so far on, it's very, very conceptual. We haven't put any math to this. Probably you're like, I don't even know, my face hurts. I don't know what questions to ask. Anybody just there? All right, let me see if I can help. One of my favorite analogies for equilibrium are escalators. Anybody when you were a kid, anytime you'd find a set of escalators, is game over. You're like, I'm gonna have so much fun on these escalators. I love escalators. I love riding escalators. But anyway, I'm thinking of, but in Buddy the Elf, isn't there an escalator scene on Elf? Yeah. Okay. Equilibrium. Here's the for sure definition if you want it. I'm not gonna, you know me, I don't just give you like vocabulary definitions on the exam, but it's a state where the forward and reverse reactions occur at the same rate. So there is no net change in the product or the reactant concentration. So on a diagram, an energy diagram, here's what equilibrium looks like. Okay. Remember we said the energy level of the reactants and the products are very similar, and you indicate the reversible reaction with this double arrow system right here. Okay. Now, I'm going to say this again. I've already said it once, but I'm going to say it again. Equilibrium does not mean equal concentrations of reactants and products. It means equal rates. So look at this mall. This is how malls in America are looking now. Nobody's there, right? We all do our shopping online. Who thinks that like in 10 or 20 years, we're just not going to have malls anymore? Everybody will shop online. Even the outdoor promenades, I'm worried about them. I don't know if the outlet stores will make it. But let's pretend that this mall is not yet obsolete. Let's pretend there's some people there. So let's pretend that we have, I don't know how many people go to malls these days. Let's say we have 500 people on the second floor. And let's say we have 250 people on the first floor. I'm just making up numbers. What you know about escalators is that they are moving at the same rate, right? So if somebody jumped on, let's say this is the down escalator, and let's say this one's the up escalator. If somebody jumped on the down escalator at the same moment that someone jumped on the up escalator, what would happen? They would reach the opposite floor at the same time, right? If they got on at the exact same second. That's what equilibrium is essentially saying. Okay, let's pretend that this is the reactant side. And let's pretend up here is the product side. I know this is a silly analogy, but I really do think it can help. It just means that you're making your reactants and your products at the same time. Does this mean we'll have the same number of people on the floor, on the first and second floor? No. If we start out with different numbers of people, we're never going to reach the same number of people on the first and second floor just by sending one person at a time to opposite floors. In fact, the numbers will stay the same. These numbers won't change. 500 people on the second floor, 250 people on the first floor. Okay. It's just that you're sending a person to the opposite floor at the same rate. Okay. That's essentially equilibrium. I don't know if that helped. I see some weird looks. Okay. Any, does that help? I don't know. I hope it helps. But if it didn't, that's why I also put this link here. I don't know if you ever used TED Ed, kind of like mini little TED Talks. If you want just somebody else to explain it to you, go to that link. It's a very short video. It's like not longer than 5 minutes. But you just copy that link, paste it in, check out that video. Maybe that will help you. It's also a very silly video, okay? But sometimes I think very simple, silly analogies that have nothing to do with chemistry and molecules can sometimes help us understand chemistry concepts. All right. Any questions so far? Okay. Well, hang on to your horses because we're not done with equilibrium yet. Here's just the definition that we had for equilibrium. And I told you that I needed to define the word concentration, right? The word concentration, I said, is a very chemistry-oriented word. And so we need to understand what it means. We're actually going to spend almost all of chapter 9 will be on the word concentration. So we're in chapter 7 right now. And when we get to chapter 9, you'll be like, oh, this sounds familiar. And it will be because I introed it here in chapter 7. So equilibrium, we said that the concentration of the reactants and products are not changing. So I'm actually going to just enter this slide right here. What does the term concentration mean? Well, it is an amount of, I'm going to use this word that we've not heard before, solute. What is solute? Anybody ever made Country Time lemonade before? It's the best, right? What you do is you take the powder, okay, and you mix it with the water and you make the lemonade. The solute here would be like the powder. It's the thing dissolving. Okay, if you're going to make a solution, lemonade is a solution. It's a mixture of more than one thing. That powder has sugar in it. It's got molecules that make it taste like lemon, kind of acidic. It's the particles being dissolved. That is your solute, okay? Per a volume on the bottom of solution. The solution is both the solvent plus the dissolved particles. The solution is the finished product. The solution of lemonade is the water and the country town powder, okay? So anyways, that's what the concentration means. Now, anybody ever had really bad lemonade at like a wedding or a shower of some kind? Yeah, it's right. It's really gross. You're like, man, they just did not put enough flavor in it. Maybe there's too much water. They made it the word we use is too dilute. Okay, so you guys are actually more familiar. Yeah, just nasty. It's gross. There's not enough of the dissolved solute, okay, the sugar and the good stuff. Okay, on the flip side, anybody ever had way too concentrated lemonade? Okay, that's nasty as well. You want just the right concentration. Okay, so the concentration is, yes, diabetes. Oh man. Okay. My mind's going so many places right now. Anyways, all that to say is that's what concentration means. It's an amount of like molecules or particles per solution, per volume of solution. There's actually two ways we communicate concentration, and you nursing majors, get ready. You're going to have to know how to do this stuff. Okay, concentrations of medications. This is how you calculate them. So you can do it as a weight volume percent, or you can do it as a molarity. All right. So weight volume percent, this is going to be grams of solute, because gram is an amount, right? Per milliliter of solution, I'm going to abbreviate. Seth said Kool-Aid's better than lemonade. Uh-oh, he's trying to start some fights here. I don't know. I like lemonade personally. Okay, molarity is moles. Is another way to convey concentration. Moles of solute per liter of solution. Okay, milliliters and liters are both fine. Aaliyah said nope, lemonade's better. It depends though. I think it depends what kind. We don't drink a ton of lemonade, but I like anything with real fruit in it. So if you took Kool-Aid and put real fruit in it, I'd drink it. But I think lemonade's really good if you put real fruit in it. All right, so these are examples of concentrations, weight, volume, percent, molarity, and these are just some units. I just wanted you to get familiar with this idea of what concentration is, because we're about to Me Too plus Arnold's. Oh, are you talking about like those Arnold Palmer drinks, whatever, like the lemonade plus the tea? Is that an Arnold? I really only drink coffee and water, so I'm out of the loop when it comes to like stuff, like different drinks. What is FYE? Are you putting in fancy abbreviations? Brennan, you've lost me.
It just means that it's good. That's what it's FI. That's funny.
Y'all it's FI. Okay, I learned what a Bugatti is this semester, and now I learned what FI is. So like if my husband eats my dinner and he's like, this is FI, that's good?
Yes.
Oh my gosh. Slang for really good. I learned what VV meant the other day. Anybody is this lecture FI for anybody? Y'all are like, no, you're not cool anymore. You could say my lecture is FI though, right? ... Okay, moving on. All right, so now that we've understood concentration, we're actually going to use concentration. This is where this lecture is about to get not FI. Okay, you're not going to like this, but we're going to actually learn how to calculate an equilibrium constant, okay? And what this is going to do, this is going to be some math here, but hang tight. What this is going to do is going to tell us about the conditions at equilibrium. Do we have a ton of reactants or do we have a ton of products? Okay, that would be important for a lot of medical reasons and standpoints that I won't get into here. But here's how we're going to do this. If we have some random reaction, A plus B makes M plus N. And what are the lowercase letters? The lowercase letters are the coefficients. Okay. Lowercase letters are coefficients. Capital letters are your reactants and your products. Okay. How we calculate an equilibrium constant, we're going to call the equilibrium constant K. We're going to calculate K. That's our equilibrium constant. Here's how we do it. You're going to take your reactants or products, the capital letters, and the concentration of the product goes on top. Now, I know we haven't even, you're not going to have to calculate concentrations. I would give you concentrations. I would say the concentration of this product is here, this number. I would say the concentration of this product is, whatever, another number. I would give you those. All you're going to do is you're going to take those and plug them into this equation, okay? And the lowercase m and n, these are the coefficients, remember? So we take the product concentrations, those go on top, and we divide the whole sum, the multiplied sum of our product concentrations by our reactant concentrations, okay? A and B are reactants here. And if you notice, M and N, the lowercase letters are put in there as exponents, okay? So you raise the concentration to the power of the exponent, if that makes sense. So this probably sounds super confusing right now. We're going to do some practice problems and you'll get the hang of it. All right, so let's say, well, real quick, before we do this, K is I think we already defined it. I think these things are just supposed to say equilibrium constant. EQUIL. Equilibrium constant. All right, that's what I forgot an N. And K tells us about the ratio. Okay, that's what I was saying earlier. Do we have a lot of reactants at equilibrium or do we have a lot of products? It tells us about the ratio of the concentration of the reactants versus products. And you may have noticed, but to indicate concentration, we put brackets. This means concentration. So anytime you see a letter or a chemical formula in brackets, what you need to plug in there is the concentration for that reactant or product, okay? K also tells us whether the forward or reverse reaction is more favorable, all right? So that is what the equilibrium constant is. That's what it does, is what it tells us, okay? It'll be a number and we'll see how that number makes sense. So here's an example. Let's say I have some reaction with actual chemical formulas and compounds now. SO2, it's a gas, plus O2, it's another gas, and we make SO3, it's also a gas. And it's balanced. We have our coefficients in there. We're going to take the concentration of SO3 because that is the product. Remember, products go on top. We would plug it in on top and we would raise it to the power of 2 because that's the coefficient for the product. On the bottom, the way we would calculate K for this reaction is we would take SO2, the concentration of SO2 and O2, put it on the bottom, and you raise it to the power of the coefficient. If your coefficient is a 1, then you don't have to do anything. You just plug that number in, okay? Because raising something to the power of 1 does not change the number mathematically. All right. So let's say I give you these two experiments. And here we have the same reaction, SO2 and O2 make SO3. Let's say for experiment 1, we're mixing okay, I got to explain this capital M really quick. 1 M, what is M? M is a unit called molarity. Earlier, when we defined units of concentration, I'll be right back. Let me go see it right here. We define molarity, okay? Molarity or weight volume percent, we said are 2 units of concentration. Molarity we abbreviate with a capital M, and it's just the moles of the dissolved substance per liter of solution, okay? So when you see a capital M here, that is the molar. That's communicating a concentration. So if we have 1 molar SO2 and 1 molar O2, what we're saying is we're starting with all reactants and no products. Okay. We have an experiment where we're starting with all reactants, no products, but at equilibrium, we find that we have these concentrations of reactants and products. So what we would do is we would just plug those in. We're going to say K equals, this is the product, so it goes on top. I'm going to put it in brackets, 0.938 molar. That's a concentration. I'm going to raise it to the power of 2 because our coefficient here is 2. On the bottom, we're going to plug in our equilibrium concentrations. 0.062 molar for SO2, and the coefficient there is 2, so I'm going to raise it to the power of 2. I'm going to plug in my equilibrium concentration of O2, which is 0.538 molar, and I have a coefficient of 1, so I don't have to plug anything in. And if you calculated this, what we would find is that K equals 425. Whoop-de-doo. What does that number mean? We'll explain that in a second. Okay, so experiment 1, we started with all reactants. Well, experiment 2, let's do it the opposite way. Let's just start with all products. And no reactants. All products, no reactants. Well, let's say at equilibrium, we find these concentrations. Notice that they're different, but we can still calculate K from that. So K would be equal to, remember, it's products over reactants. So here's our concentration for the product that goes on top, 0.850 molar. And we're going to square it because the coefficient for that product is 2. On bottom, we put in the equilibrium concentrations of our 2 reactants. So that is 0.15 molar. This is for SO2. That's the first reactant. And we're going to square it because of the coefficient of 2 on that one. Times the concentration of our second reactant, oxygen, over here, 0.0751 molar. And we do not raise it to the power of anything because the coefficient is 1. And if you did this and threw that in your calculator, you should find that K is 428. All right. Now, I know you're like, you told me K was a constant, and here are the numbers. Caroline said, whoa, I can't write that fast. Okay, I'm slowing down. I'm going to talk for just a second. K is essentially a constant. Every experiment has a small amount of error because we're human. Even when we use instruments and fancy technical equipment, it's not perfect either. So here, what you would say is K is within our experimental error, and we still can consider K to be a constant for this reaction, essentially the same number. Not phi. I know, I agree. I don't love equilibrium either, but it is part of the content course stuff that we have to cover. Whether we like it or not. Okay, it's like eating green peas. Anybody? I hate green peas. If you had to pick a least favorite vegetable, what is it for you? For me, it's green peas. I don't ever cook them. You love them? Leah,
Carrots, those are the worst.
Carrots are the worst? Carrots aren't the worst. My 2-year-old will eat a whole plate. Cauliflower, I agree. That's disgusting, Seth. Why would anyone ever eat cauliflower? You people who eat your cauliflower crust pizza, more power to you. All right, well, that's what equilibrium is. It's eating your vegetables. It's good for you, but it's not fun. All right, so what does all this mean? Caroline, are you caught up? Okay, sweet potato, Olivia. Come on, sweet potato is good. Caitlin says, thank you, Caitlin, for this. I'm not understanding why you wrote all reactants, no products, and all products, no reactants. Where are we using all parts of the equation in the problem? Same. Thank you. Thank you for asking your questions. I need these. We're looking, the reason I wrote that, Caitlin, is because we're doing an experiment. Let's say we have a test tube, and in that test tube, we just put SO2 and O2. Okay, we're going to mix 1 molar with 1 molar. What that means is we have no products here. We're just going to mix the reactants together. and we're going to see what happens. At equilibrium, how much of the reactants and how much of the products do we have? Okay. And then we're going to do a reaction from the opposite direction. We're going to start with just SO3, which is a product in this reaction, right? SO3 is over here on the product side. So essentially, we're doing the reaction from two different directions, if that makes sense. And what we find is that even when we approach the same reaction from two different directions, we end up with the same equilibrium constant. Okay, now I know I have not explained what these numbers mean yet. And unfortunately, we're about out of time. So it's like I'm leaving you on a huge cliff ledge. Okay, anybody watch Harry Potter movie number 7 and they broke it up into 2 movies and they left you on that huge cliff ledge where Voldemort holds the wand up in the air and you're like, no, now I have to wait for the second movie. That's today. So, okay, I have another question. What's your question? Oh, first of all, Caitlin, Allison, anybody else who had that question? Did that make sense what I just said? Did that answer your question? You could be honest if you're like, I'm still confused. Okay, that helps. Good. Okay. Caroline, what's your question?
Okay, so the squared is the moles, right, that you have of that thing?
The squared is just we're taking the coefficient. And
Yes.
we're plugging that in as the exponent.
Yes. So when it says to start with 1 mole of SO3, like on number 2, do we still put like the 2 up top, even though you're starting with 1
Well,
mole?
you're not ever going to plug in your initial concentrations to the equation for K. You're always plugging in the equilibrium concentrations. So like once the reaction runs, and it settles out, okay, think about the escalators, it settles with a certain number of reactants and certain number of products. Now we just have the forward and reverse reaction happening at the same rate, the escalator idea. And what we're going to plug in, we're going to recheck the concentrations and we'll plug in those. So at equilibrium. So we'll never plug in the initial conditions. You'll always just plug in your so you're not going to actually do anything with the 1 molar.
Okay.
That's just what you started with. I just wanted you to see we were approaching this reaction from 2 different directions.
Okay.
Okay. So what we'll do, this slide is actually the best slide. So we really are ending at the worst point, but I don't want to go over on time. So we will pick up here. I'm going to make a video because we're out of lecture time for chapter 7. I'm going to make a video that picks up here and I will post this video by tonight and it'll finish equilibrium. Okay. We were almost done. Two or 3 slides left on equilibrium. And then I will post a separate video entirely on Le Chatelier's principle. Okay. So watch those before Monday. And then we'll be ready to do lab for next week. Okay. All right. Brains fried enough? Okay. Well, thank you for joining us today. If you have any questions, I will stick around and answer those. If not, I will see you next week in lab. And I mean, I'll actually see you. Looking forward to hanging out.